and welcome back to another lecture of statistics, 479 time series analysis. In this lecture, we'll be doing, well, Arima once again, but now it's seasonal Arima because the seasons are changing and we need to talk about seasonal models for time series. So effectively, everything we're going to be doing in today's lecture is exactly the same as what we did with Arima, but we're going to consider the fact that there could be seasonal trends. That is, for example, the weather. The weather gets hotter in the summer, colder in the winter, and if we look at the weather year on year on year, we would expect to see the same type of trend. There's going to be local fluctuations, of course, but we would imagine that the summer of last summer is correlated with this summer and will be correlated with next summer, and similar to the winters. And what we're going to do is we're going to look at how to fit a seasonal time series model, specifically a seasonal Arima model, in order to analyze these types of periodic trends in time series. So let's go take a look at the notes. And welcome back to another lecture of Statistics 479 time series analysis. Today we're going to be, well, in some sense, just doing AR and Arma and Arima again, but in this case, we're going to be looking at seasonal models. So all of the models that are all subsetting from the Arima model, the AR, the MA, the Arma, and so on, we can also think of them as being seasonal models. So intuitively, seasonal models, kind of make a lot of sense. So let's imagine an example, like say we want to look at the price or the sales at a retail store. Let's say a clothing store or something. So watching the sales, say, I don't know, monthly or even daily, let's say throughout the year, what we'd expect is perhaps in December there to be an increase. People are shopping for Christmas time, say. Then maybe a drop in January. Maybe there's another increase when the seasons change into the summer. People want to go buy new clothes for the summer or back to school in the fall. So you could imagine that throughout the year, you might see little ups and downs in the purchases of clothing, say. Now, if we watch this over many years, we would expect to see the same spikes at the same time points. Every December, we'd still expect the shopping to go up for Christmas and then down in January and so on. And this is where we get into the idea of a seasonal Arima model, where what we're going to be doing is we're going to be, well, just trying to fit an Arima model as usual, but looking for periodic trends. And this is very, very common in time series data. It could be monthly or annual or even weekly cycles that you might see in your data. And it's really good to identify them because it can help us in better understanding the time series data that we're looking at. I guess an even easier example than clothing sales would be temperatures, right? If we're measuring the average temperature in Edmonton, or let's say the daily high temperature, for example, in Edmonton, we'd expect it to go up in the summer and down in the winter every year. So if we're watching many years over time, then we'd again expect some type of a seasonal trend in our data. So how do we model that? Well, let's go look at the notes and we will sort that all out. All right, so in this lecture, as I mentioned, we will be discussing the idea of seasonal Arima models. Underline. Okay, so as I mentioned in the introduction, we can effectively take any Arima model that we've already discussed and add a seasonal. Think of it as a seasonal model. That is, take the context, that is the equations for an Arima model, and then turn it into a seasonal one. So instead of just having an Arima model, we might have one that has a seasonal period of length 2, or maybe length 12 if we're doing every month, or length 7 if we're doing every week, for example. But let's write out some examples. So the first thing is we can have our usual AR1 process. That's just going to be xt is equal to phi xt minus 1 plus wt, right? I've written this a lot of times. But if this is, let's say, say t is equal to months. So let's say that t indicates a month of the year, and we're watching some autoregressive process where we're taking a measurement every month. Again, maybe it's average temperature. I don't know if an AR1 process would be a good model for average monthly temperature, but let's just pretend as an example this is what it might be. But the idea is that we could also consider a seasonal AR1 model. I can write that correctly. AR1 model. And in this case, we could say maybe not, well, seasonal, but maybe what we can say is annual. Again, we could have different periods for our season. And well, there we go. Got the words right. In this case, what we might have is something that looks like xt is equal to phi xt. And now instead of -1, I'm going to put -12. And there's my seasonal model. It looks a whole lot like an AR1. In some sense, it's like an AR12, but with phi 1 equal to all the way up to phi 11, all being 0. So to a certain extent, it's just another autoregressive model. But it's a very special one. We don't want to think of it as a general order 12 autoregressive model, because that in some sense implies that there would be other coefficients that may be non-zero. If we try to fit an AR model to data that has let's say a cycle or a season of length 12, then we'd still be trying to fit these other phis here. And we probably don't want to do that. Instead, we'd want to target the idea that we have a model with a specific cycle length or period length here hidden within it. So then, of course, the question's going to be, well, how do we determine a good length for our seasonal components for our model? But that's a whole nother thing. Right now, we just want to stare at this and say, okay, I have an AR process and it's going to have a period of 12. So if we were to actually look at this data, well, what it might look like, let's say we have 1, 2, 3, 12, 13, 14, and so on, then we might be observing, say, time series points like this. And the idea is that we have an autoregressive process, but what we're doing is we're linking points that are 12 time units apart. So in some sense, in this pure seasonal AR1, I'll say seasonal AR1 model, here, effectively the points in between 1 and 13 don't, in some sense, interact with each other. What we're saying is that the value at time 1 is going to affect the value at time 13, and 2 is going to affect the value at 14, and 3 at 15, and so on. So in some sense, this is like, we'll say, like having 12 independent AR1s running together. Because if you look at the dependencies here, if I have a model like this seasonal AR1 that I wrote at the top, effectively I have 12 different AR processes, one that starts at time 1, one that starts at time 2, and all the way up to the one that starts at time 12. And none of them, in some sense, are interacting with each other stochastically. They depend on the 0.12 time points into the past, and they have some white noise, which is uncorrelated and only sort of exists in the given time point t. Otherwise, it's not interacting with other time points. So in this very specific case, the points in some sense are not talking to each other locally. Now, this is an extreme case. Typically, you might have a mixed model where you have some seasonal component and you have some non-seasonal component. But in this pure case, we're basically running 12 AR processes sort of in parallel or kind of offset from each other. So it's a good thing just to imagine what's going on there. Now, in general, what we do is we write that xt is going to equal phi xt minus s plus wt. And what we're going to call this is an AR1. And then we're going to put a subscript s down here. So make sure that's you kind of see that there's a little subscript s hiding here. This is going to be an AR1 process with a season whose period is s. So that could be 12, it could be 2, it could be 50, it could be 365, right? It's just the seasonal component period, that's the length of the season. And we're assuming that the length is fixed throughout the time series, so we're not going to have any kind of variable season lengths. It's kind of interesting. I'm not sure if anyone's ever investigated that or if there's even data that would have variable season lengths, but in this case, we're not going to be dealing with anything like that. We're going to have a fixed period for our season. And then furthermore, continuing with our in general, what we can do is we also write an Arma, man, I have lots of typos. Arma, what I'm going to write is P prime, Q prime, and S. And this is a seasonal Arma with period S and AR order P prime and MA order Q prime. Now we use the primes because we're eventually going to try to combine a non-seasonal autoregressive or Arma model with a seasonal Arma model, and we need to make sure that we don't can't use the variable P, because we can have a different order P prime for our seasonal model than for our non-seasonal model. So now there's going to be a lot more parameters that we're going to need to fit in our model. So mathematically, what we write this as is in an equation form, we still have an autoregressive operator. Now I'm going to do phi sub s with a b, and then I'm going to take this to the s power. Good thing I have the filter here, or that would be a lot of air blowing into the mic. And then we'd have the moving average piece on the right-hand side, theta sub s and b to the s power applied to wt. And again, here we're assuming mean 0 and all of that. I guess the non-zero mean could be factored into this if we really wanted to, but again, it's usually easier just to ignore the mean so that we don't have to deal with that extra piece of the equation. Anyway, it's exactly the Arma model. The only difference is that we're effectively plugging in a b to the s power here. So that means that if we had, say, something like if phi of s be s, for example, let's say e.g. could be something like I don't know, 1 plus phi, or maybe minus phi to keep with the notation from above, phi 1 b s plus phi 2 b s square, or b2s, and so on. You know, we could have something like that. So it just means that we're doing an Arma process, but we're kind of increasing the gap between the current time point and the next relevant time point, which is now either s units back in time or 2s units or so on. But beyond that, it's really just the same thing. And if we were to just ignore all the intermediate time points, it would just be an ARMA process. But we're also going to have, we're going to be trying to combine this with a non-seasonal component. Oh, yes. So we also need, actually, I should probably change the notation, because I see in my written notes that I need to be a little bit more careful about the notation, because we need to make sure our parameters don't conflict with each other. So here what we'll do is we will write phi s b to the s power as something like 1 minus script phi 1 b s, and then minus script phi 2 b 2 s, minus all the way down to our p prime b to the p prime times s. And similarly for theta, in this case, we just need to identify, because we want to make sure that our parameters, we know what all of our parameters are. So here we're going to need a script theta, which let's see if I can draw that. Yeah, it looks pretty good. Again, BS, and I need to think if I'm going to do this well. There we go. This is 2s, and so on, all the way down to script theta, not 3, q prime b to the q prime s. So what I'll say is forget about this one up here, because I don't want it to be confusing, because eventually we want to use regular phi and regular theta as our non-seasonal ARMA parameters, and script phi and script theta as our seasonal ARMA parameters. There's going to be a lot of parameters in this model. I guess assuming p and q and p prime and q prime are big. So basically we can combine a seasonal and non-seasonal, the thing we've been talking about for the entire course up till now, ARMA. And what we get is going to be something that's going to be denoted as ARMA PQ, and then crossed with P prime Q prime S. So now we have that. And if we write this out using the equation like we did up here with our operators, we're going to end up with 2 operators on the left and 2 operators on the right. So mathematically, what we're doing is we first apply, I guess not first, it's actually second, but if we're writing from left to right, we're going to have our seasonal autoregressive operator. We're going to have our non-seasonal autoregressive operator, and both of these are going to apply to X. And then on the right-hand side, we're going to have our seasonal moving average operator, our non-seasonal moving average operator, and apply that to WT. So here we have, again, this is seasonal AR operator, regular AR, non-seasonal, seasonal MA, and regular MA classic. There we go. So this is what we have. And mathematically, it's nothing, it's annoying to look at, but it's really nothing that profoundly different than what we did before. We just have even more operators getting multiplied together. We have a whole bunch of backshifts. So now we're going to have like X's and X's backshifted to different times and also seasonally. But ultimately, there's nothing too different going on there. And one more thing before we'll be doing some examples, and we'll definitely look at some data, so don't worry about that. But we can also do an Arima. So we can actually do a seasonal Arima model, and now we can have PD Q, right? So that's the autoregressive, the differencing, and the moving average. And we can, if I can write, we can have a P prime, D prime, Q prime. So now we can have seasonal oh, and we need a subscript S here, which is going to be the period. So now we can do seasonal differencing as well as non-seasonal differencing. And we'll write this all out. And what we get is something that's going to look like phi S, B to the S, phi B. And then what we're going to do is apply the seasonal difference operator, which we're going to call, I guess, nabla sub S to the D prime. And then the regular differencing operator, which is just our nabla to the D. I wonder what the origin of nabla is, right? It's just such a, I do not know where that comes from. We're going to have to look that up later because I do not know. I always want to say delta, but it's not delta. It's nabla. It's upside down delta. Anyway, yeah, we have our moving average piece here. That remains unchanged from the above. So now we get a seasonal differencing, and we get a non-seasonal or regular differencing. All right, so then the thought is, well, actually, I should probably just make sure I define what those operators are, just so that we're clear, right? Just going back to the regular differencing operator. The regular differencing operator is a 1 minus B, the backshift operator, and it's taken to the dth power. Whereas the seasonal differencing is kind of what you'd expect it to be based on the other equations. It's 1 minus B, but taken to the s power, and then taken the whole thing to the dth power. The d prime prime. Yeah, to make sure that we indicate that these are different orders. All right, so we've got a lot of things to deal with here. Luckily, there are packages that'll just do it for you, but it is good to understand what's going on here. So what I'll say is note the auto dot Arima function in forecast, the forecast package, can select a seasonal model for you. So I think there are other ways that you could probably manually fit a seasonal model. I would have to double check to see which R packages allow for seasonal models and which have not implemented it or not. The Auto Arima will try to check some seasonal models. In fact, if you look at the documentation in that function, they even allow you to switch like a Boolean variable to switch whether you want to consider or not consider seasonal models. If you do consider seasonal models, the runtime is a lot longer. I mean, if you don't consider seasonal models, it's almost instantaneous, I guess, unless maybe you have a really big time series. If you do consider seasonal models, it can take a little bit longer to compute, but it will find a good seasonal model for you. And we'll be doing that later. We will be looking at different R packages you can use to fit these and do estimation and forecasting and model comparison with AIC and BIC and all the fun stuff that we've done so far for the Arma, the AR, the Arima, the MA. We can do it for this as well. I also wanted to point out that sometimes you'll see people write, where's a good color to use? We'll use blue. Sometimes people will put an S in front of this and call it a SARIMA model for a seasonal auto-regressive integrated moving average. That's a good acronym. So just so you know the terminology, if somebody says SARIMA, they might be referring to a seasonal Arima model. You have to be a little careful though, because it doesn't work for other things like tangent, SAR, is not a seasonal autoregressive, but this is sometimes a simultaneous AR from spatial statistics, which is like non-causal spatial time series models. So you can't always, I mean, sometimes there could be some ambiguity. If you say an SAR, that might not necessarily be a simultaneous, or it might not be a seasonal AR, but it could be a simultaneous AR. So the acronyms aren't great, but at least Arima, I think, usually just is a seasonal Arima model. All right, so now that we've, kind of done a lot of that, let's do an example of, well, the one that I just wrote down, the seasonal Arima, or seasonal autoregressive. So let's consider the seasonal AR process, because it's always good to start with something a little bit easier as an example. And we're going to start with the same thing that I wrote up above, which is going to just be, I guess, phi x t minus 12 plus wt. So we're going to try to understand what this thing is doing. All right, so the seasonal autoregressive model. Now, the first thing I want to do is I want to change the notation and change this to a script phi to try to coincide with what I wrote above, just so we indicate that we have something different in case we want to combine this with a non-seasonal autoregressive process. And as with the usual AR1, the non-seasonal AR1, we want our parameter script phi to be less than 1 in magnitude, just as we did before, so that we have a stationary causal process. Otherwise, yeah, we're going to run into some trouble. Now, we can write this in different ways. We can write this in terms of the autoregressive operator as 1 minus phi b to the 12th power applied to xt is equal to wt. So this is one way that we can write this. Now, what does the auto covariance look like? Because if you've learned anything in this course, you've learned that really everything we're doing is based on the auto covariance function. So we probably want to figure out what the auto covariance looks like in this case. So to compute the auto covariance, well, what do? Well, what we do is let's start with the model as I wrote above, and let's do what we did way back in, I forget, like one of the first lectures. Why don't we just apply the definition recursively and see what happens? So I am not writing subscripts here. That is not good. We need our subscripts t minus 12 and wt. So if I apply this definition recursively, I end up with a phi x t minus, well, 24, I guess, plus wt minus 12 plus wt, something like that, which, if we expand this, is going to be a phi squared x t minus 24 plus, I guess, phi squared wt minus 12 plus wt. Not phi squared, just phi itself. All right, so if we do this, I guess, infinitely, using the fact that phi is less than 1 in magnitude, so this first term is going to end up vanishing because it's going to tend to 0 geometrically, then what we're left with is going to be a summation of all the white noise pieces. We're going to take j from 0 to infinity, but now we have something slightly different. We have script phi to the jth power. That's the same as before, but the index for our white noise is now going to be minus 12 times j. So besides the minus 12, this is basically almost the same as before, where what we would have gotten is something like xt is equal to the sum j from, I think, 0 to infinity of non-script phi to the jth power wt minus j. Right, this is the causal linear process form, as just to re-emphasize that. Causal linear process. Excellent. All right. Well, we can just compute the variance. So the variance of xt is going to be the same as it always is, right? In this case, what we're going to do is we're going to apply the variance again. If you're happy with the previous lectures where we kind of discussed why I'm allowed to do this mathematically, we can just apply the variance to each term here. We're going to get a script phi squared j. Consider the variance of my wt minus 12j. And it doesn't matter that I have a seasonal component because I'm still summing to infinity, which means I'm going to get my, not an equal sign there, I'm going to have sigma squared, the variance of the white noise process, times this geometric series. And this geometric series is just going to give us exactly what we had before, which is 1 minus phi squared. Yep, so there's our variance. Now we have some different things happening, though. So if we want to compute, again, this is kx at lag 0 is the variance. If we wanted to compute kx at lag h, let's say h equal to 1 to 11, or it's in, let's say, the values of 1 to 11, well, actually even 12, I think, lags, sorry. Yeah, lags from 1 to 11. Then what happens? Well, let's just use the linear process definition or form of our series here and just kind of fight our way through the mathematics. So when I want to do this, I'm computing the covariance here between two infinite sums. One is going to be j from 0 to infinity of phi to the jth power wt minus 12j, just like it is up in the blue box. And then we're going to do the same thing. J from 0 to infinity, phi to the jth power, wt, but now I'm going to subtract an h. I'm going to lag it back by h units, and I'm still going to have a minus 12j there. Okay. Well, again, the covariance is bilinear. So if we are happy with the convergence of these infinite series, then again, phi is less than 1 in magnitude. We have the geometric convergence. We're all good with all that. What we're going to do is we're going to swap everything. And we're going to end up with something like the sum I from, I think, 0 to infinity. The sum j from 0 to infinity. And then we're going to combine phi j, phi I, get multiplied together to get phi to the j plus I, and then we're going to take the covariance of the thing on the w's. wt minus 12j and wt minus h minus 12j. Okay, so what are these covariances? Well, they're all 0, right? They're only going to be non-zero if the two indices equal each other. So, right, this thing, let's kind of like just note that the covariance of wt and ws is going to equal, right, sigma squared if t is equal to s, and it's going to equal 0 if t is not equal to s. Well, the problem here is that these two things are never equal to each other, right? So here, what we have is we have a t minus 12j, when is that going to be equal to t minus h minus 12? Oh, I should have an I in there, sorry. Just to, we'll say 12I. Yes, so in this case, if we cancel out the t's and we move around, rearrange the terms a little bit, what we're going to end up with is something like h has to be a multiple of 12. Well, it can't be a multiple of 12 because we specified that it's somewhere between 1 and 11. Therefore, this condition here never happens, and therefore this is going to equal 0. And in fact, it's not just h from 1 to 11, it's any lag that is not a multiple of 12. So the point is that we actually have that kxh is equal to 0 for all h not divisible by 12. In this example, right, we could replace 12 with s. I'm just using 12 because, again, it's a very natural season to have, period to have for your seasonal model. If you have monthly data, which is often a case that you'll run across with real data. All right, so then what happens when h is a multiple of 12? If h is equal to, let's say, 12 times something, 12 times, I need another letter now. We'll just say 12 times r and hope that I don't get myself into trouble using r. I don't think I'm going to get myself into trouble. Then, well, what happens? Well, in this case, what we're going to get is effectively the same thing we did in the AR1 case. So we can do a specific example first, which is going to be kx at lag 12. If we do this, then going back up to, where are we? This formula up here. So if we use that same formula holds, but now we're going to have indices that actually equal each other. And what we're going to end up with is something that's going to look like sigma squared phi times the sum j from 0 to infinity of phi to the 2j. And in this case, we're just going to get sigma squared phi over 1 minus phi squared. And we can effectively extrapolate this idea to say that if I have some multiple m of 12, I'm going to get the exact same thing, but I'm going to be taking the phi in the numerator to the mth power. And we have what the auto covariance looks like. So again, this is identical to the auto covariance for some process yt equal to phi yt minus 1 plus wt. If we only look at every 12th lag. So again, that's why I keep emphasizing that if we just have a purely seasonal AR process, what it's going to look like is it's just going to look like 12 independent, or at least uncorrelated, depending on our choice in white noise, 12 uncorrelated AR1 processes that are all offset by some, number 1 through 11, I guess. Like I said, the main point to take away is the key point is don't fit an AR12 to an AR112. This is something just to keep in mind. Like I said before, if we have an autoregressive process that's an AR1 with a season of length 12, that's one parameter we have to worry about. But if we try to fit an AR12 model to it, the Yule-Walker equation, maximum likelihood, whatever method you're using, is going to try to fit 12 different parameters, and you're going to have way too many parameters for your model. Now, you might be able to identify the fact that many of them look like they should be 0, but it's better to use methods that will try to identify a seasonal model rather than just fitting a really big autoregressive model. Because again, technically, all these seasonal models are just autoregressive models. We're just making and emphasizing that the intermediate parameters are all equal to 0. All right, so why don't we look at something a little bit more interesting? Let's look at a seasonal Arma process. And in this case, what we're actually going to do is we'll do a mixed seasonal Arma process to try to see what happens if we try to mix a little bit of both of them. So in this case, we're going to consider a model that is going to be an Arma, let's see, an Arma 0, 1 crossed with a 1, 0, 12. So what should that look like? Well, what it's going to look like is it's going to look like this is a non-seasonal MA 1, and this is a seasonal AR1 with a period of 12. So we're going to take a seasonal autoregressive and combine it with a non-seasonal moving average. So what does that equation look like? Like I said, there's nothing too sort of profound about all of these, but I think it's useful just to write them out so that we can get a sense of what they look like mathematically and how they behave. So we'd still have the same seasonal autoregressive operator that we had in the previous example. And then on the right-hand side, we would have our non-seasonal moving average operator, which is going to be a non-script theta here, just to emphasize. That looks like this. So if we were to, undo the operator notation, we would end up with something that looks like xt is equal to the seasonal xt minus 12 plus theta wt minus 1 plus wt. All right, so what can we learn about this process? Well, let's see. First of all, we should probably do what we always want to do. Let's compute the variance and let's compute the auto covariance and see if we can make some sense out of what that tells us. So the auto covariance in this case, or I should say the variance, kx at lag 0, which is just the variance of the process, xt. Here we're again assuming that phi is and theta. I should just put that in just to emphasize that we want phi to be less than 1 in magnitude and we want theta to be less than 1 in magnitude. So we have a causal invertible Arma process here. Otherwise, again, we could run into some trouble. So we're going to make sure that we keep that the way we like it. Okay, so what happens when we try to do this? Well, let's just plug in the definition and see what comes out. So here what we're going to get is we're going to get the variance of phi. When I say definition, I mean plug in this equation right here into the variance and see what happens. All right, so we get something that looks like this. All right, so how do we compute the variance of this guy? Well, what we can do, right, the variance is kind of an expectation of that thing squared. We're assuming it's mean 0. What we can do is we can actually break it up and take the variance of each piece. So what we can do is we can say that this is going to be the variance of phi xt minus 12, the variance of theta wt minus 1, and the variance of wt. So why can we do that? Well, all of these three terms are uncorrelated, right? wt is white noise. It only depends on things at time t. wt minus 1 happened one time point into the past. So wt and wt minus 1 are certainly not correlated because we always, at the minimum, we assume that our white noise is uncorrelated. We often assume stronger that it's right, independent, that it's Gaussian, etc. But at the minimum, these two white noise terms have to be uncorrelated. Also, xt minus 12 is an observation 12 time points into the past, which means any white noise that happens in the future of that time point is going to be uncorrelated with it, right? Because xt is a causal process. It only depends on things at time point t minus 12 and into the past. Since both wt minus 1 and wt lie in its future, if that makes sense, they are also uncorrelated. So all of these three things are uncorrelated with each other. And from here, we just compute. We get a phi squared times the, times the variance, right? The variance is stationary here of xt, so we get something that looks like that. Over here, I'm going to get a theta squared, and the variance of the white noise process is just sigma squared. And lastly, I'm just going to get another sigma squared. Now, what we do is we factor this out and we rearrange the pieces. And what we get is that the variance of the process is going to look something like what? It's going to be sigma squared 1 plus theta squared divided by 1 minus phi squared. Yep, that looks good. All right, so that's going to be the variance of our mixed seasonal Arma process in this case, the 0, 1, 1, 0 with a period of 12, even though the period in this case does not affect our variance. I guess it would if we had a period of, well, no, even if we had a period of 2, it wouldn't matter unless we had a period of 2 and an MA2, because then there could be some non-vanishing correlation between the seasonal part and the non-seasonal part, which would be a little bit strange. But right now we're good. We're good. All right, so what about the auto covariances for lags that are not 0? So this is the first thing. Then the next thing we want to look at is if h is equal to 12. Here I use 12 times m, so I'm going to try to keep with the notation that I picked in this lecture and use 12 times r. So again, if h is a multiple of 12. Okay, so if h is a multiple of 12, well, then what happens? Well, we're going to get kx at lag h is just going to be kx at 12 times r. And what we're going to get is we're going to get kind of the, well, we're going to get two things. I'm trying to think I know what the answer is, but I'm trying to figure out the right way to explain it, right? Well, here, I'll write down the answer and then we'll stare at that. So it's going to be something like sigma squared, phi to the r, 1 minus phi squared. Okay, so what happened to the moving average piece? Well, I'll say recall that for an MA1 process, let's say YT is equal to theta WT minus 1 plus WT. What do we know about that? We've computed the auto covariance for that a lot, right? The auto covariance for this thing, well, at lag 0, it's going to be 1 plus theta squared for h equals 0. It's going to be just theta at h is equal to 1, and it's going to be 0 for h greater than or equal to 2. So effectively, if h is a multiple of, I guess I should emphasize r, just to be precise, I should say r greater than or equal to 1. If r is equal to 0, we get the variance, and that 1 plus theta squared term pops back in. But in this case, we don't have that happening. Instead, what we have is the moving average piece no longer has any influence. That is, there's no correlation once we move beyond a lag of 1. When we're at a lag of 2 or higher, it doesn't affect anything. That is contributing 0 in some sense to the auto covariance. Instead, we just have the moving average, or the autoregressive piece, and that's going to be exactly what I found, I think, right up here, except that I did use M. Huh, that's really funny. And I had M in my mind, right? And then I'm like, I'll use R instead, but then I ended up writing M. So maybe what we'll do is we'll just change these all to M's. And then they coincide with what I had written in my notes. It doesn't really matter, but right, we just need to be consistent throughout the lecture. And we'll make this a green M. Luckily, I can turn an R into an M pretty quickly. Excellent. Okay, so remember, this is roughly what's going on here. But then we also need to think about what happens at lags between. So what about lags between 0 and 12 and 24 and etc. 12 times M. So if we have a lag that lies somewhere in between 0 and 12, or that is 2 multiples of 12, if it's not divisible by 12, but it's not, well, I guess 0 is technically divisible by 12. If it's not divisible by 12, then we have to figure out, well, what's going on there? So, well, there's a couple things that happen. First of all, let's consider, I guess, if h is going to equal, all right, let's do 2, 3, up to 10 mod 12. So again, this is mod 12. If you haven't seen modular arithmetic, that just means reduce. It's the remainder. So it basically means take h, divide by 12, and get the remainder. I mean, a lot of you, if you're taking a math degree or a stats degree in a math department, have probably seen modular arithmetic somewhere. But just in case, the idea of saying mod 12 says just reduce h by 12 and divide by 12, and then take the remainder that's left over. So if h is equal to 27, we divide by 12, we would get 2 and whatever's left over, which I guess would be 3/12. So 27 would equal, we'll do that, I'll write that out. E.g., 27 is equal to 3 mod 12. Just to indicate. So what I'm trying to get at is that if we have lags that are between 2 and 10, then, well, what happens? For the AR piece, then we know that K, X, H, well, it's going to be the covariance, but if we just kind of intuitively think about this, right, what's going to happen? Well, the MA1 is going to contribute a 0, right, because the lag is greater than 1, and the AR112 is also going to contribute a 0 because it only cares about lags that are multiples of 12. So in this case, all of these are actually going to be 0, so we're going to get no correlations there. Yes, but we're still going to have to consider what happens when H is equal to 1 or 11 mod 12. And here we have to kind of work out what's going to happen. So the easiest way to think about this is just start with, well, 2 examples. The first would be Kx at lag 1. So that's a good one to try to just compute by hand and see what happens. Well, in this case, what we're doing is we are computing, well, the expected value. Again, we're assuming that it's mean 0, so we're going to compute the expected value of xt and xt minus 1. Right, that's just the auto covariance at lag 1. Well, what we can do is we can apply the definition of xt, which is somewhere up there off the top of the page, but luckily I remember it. Hope I remember it. It is phi x t minus 12 plus theta w t minus 1 plus wt, and we're applying this or multiplying this by xt minus 1. All right, so what can we figure out from here, right? Well, what we get a couple things. Let's break up this expectation linearly. Here we're going to get something like phi times the expected value x t minus 12 x t minus 1. Then we're going to get theta, the expected value of x t minus 1 w t minus 1. And then we're going to get the expected value of wt x t minus 1. So those are the 3 things we got to deal with. The first one is another auto covariance. At this point, it's the auto covariance at lag 11, and hence why I started this section by pointing out that we have to consider both 11 and 1. But okay, so we have this at lag 11. What's this other piece going to be, this middle piece? Well, this one is a little bit maybe not straightforward. What it's going to be is sigma squared theta. I'll explain that in 1 second. I also just want to write down that the expectation, the third expectation here, is going to be 0. And that's once again because wt lies in the future of xt minus 1. Xt minus 1 is a causal process. These things are uncorrelated. This thing goes away. Now, just to emphasize where this came from, why we ended up with a sigma squared for the middle term here, if we consider the expected value of xt minus 1 wt minus 1, if we again apply the definition of this time series, we replace xt minus 1 with a phi xt minus 13, because we're starting at t minus 1 and subtracting another 12 from it. Then we're going to get a theta, or not x, a theta w t minus 2 and a wt minus 1, all times wt minus 1. And the point is that this guy is uncorrelated with these other 2 terms. The only thing that matters is this one. And when I compute the expected value of w t minus 1 squared, I end up with sigma squared. So that's where the sigma squared comes from here. Okay, so we don't know what the auto covariance is yet. We just know that the auto covariance at lag 1 is somehow related to the auto covariance at lag 11. Well, let's try to compute the auto covariance at lag 11 and see if that helps us. Spoiler alert, it will. Yeah, we can just do that. And let's start above. Just like I did above, we're going to do the exact same type of expected value. In this case, I'll say xt times xt minus 11, and then just kind of, well, fight through the whole thing again. What we end up with is an expected value of, using the definition of the process, phi x t minus 12, let's see, plus theta w t minus 1 plus wt, and we're multiplying this by xt minus 11. Now, if I break this into pieces, we get a phi, an expected value of xt minus 12, xt minus 11. We're going to get a theta expected value, wt minus 1, xt minus 11, and lastly, an expected value of wt xt minus 11. Well, we are in luck because the last two terms are both going to be 0. Right, they're going to be 0 for the same reason why all these terms keep becoming 0, because the white noise lives in the future of the process xt minus 11, and xt minus 11 is causal. It only can be correlated with things that are in the present or in the past of its time. Wt minus 1 and wt are in the future. These things are both 0. And the first term just so happens to be, well, the auto covariance at lag 1. Again, stationarity is wonderful because it allows us to do all of this. If the process weren't stationary, we'd be doomed. Can't do any of this. But it is stationary, so we got all this. So this is great because now what we can do is we have two equations that we can combine. So now we have two equations to consider. The first, which is about running off the top of the page here, is that kx at lag 1 is going to be phi kx at lag 11 plus some term that does not depend on the auto covariance. Well, I guess it's not in terms of k, I should say. And then we find out that kx at lag 11 is going to be phi kx at lag 1. All right, so we can just basically plug it in and go, right? If we know what kx1 is, so what we do is we combine these two things. And, well, what do we get? Well, we get that kx at lag 1 is going to equal phi times, well, kx at lag 11, which is just phi kx at lag 1. And then we're going to also get a plus sigma squared theta here. So if we solve for this and rearrange the equations, we find out that kx at lag 1 should be sigma squared theta divided by 1 minus phi squared. All right, we got something. And what else do we get? Well, what else do we get? We also get that at lag 11, we get phi times, well, that thing that I just wrote down, kx at lag 1. So we end up with just a sigma squared, a theta, a phi, and a 1 minus phi squared. All right, so that's kind of neat. So what can we do from here? Well, if we want to, we can then extend onward beyond 1 and 11, right? Because what we ultimately wanted was not just the auto covariance at lag 1 and the auto covariance at lag 11, but we were interested in all h that are either equal to 1 or 11 mod 12. So the next thing we might be interested in is h is equal to 13. So let's try that and see what happens and, get a pattern inside our head as to what's going on here. Well, if we want to know what happens at 13, well, we can do this exactly as before. In this case, if we go back to what happened with lag 11, we're going to get the exact same thing here, but with a 13. xt minus 13, and the exact same issues are going to occur, except that in this case I'm going to reduce this down to something that's going to look like phi x t minus 12 x t minus 13. By the symmetry, right, this is just going to be, well, the same thing. It's the exact same thing as lag 11. So it's actually equal. At lag 11 and at lag 13, we get the same auto covariance, which is taking, in some sense, the, man, where is that? Oh, it's way up here. It's the auto covariance at a multiple of 12. Notice this equation here in the red box, and we're multiplying that thing by theta. So all we're doing is we're saying, okay, if we're a multiple of 12, we have this thing that's going to look like phi divided by 1 minus phi squared, and there's always a sigma squared in the front there. If we're 1 off from that, we're going to be multiplying by theta. If we're 2 or more off, then we're going to multiply by 0, unless we're so far off that we're now a multiple of 12 again. But yeah. So in general, what we can show, we have that k x at lag 12 m plus or minus 1 is going to equal to, well, the expected value of xt minus 12 plus or minus 1. If we go through this whole thing again that we did, we'll end up with something that's going to look like phi k x. So actually, why don't I write it out the right? We'll just not skip that step. It's going to be xt minus 12 xt minus 12 plus or I should be 12 m, sorry. 12 m plus or minus 1, 12 m plus or minus 1. When I look at that, it's just going to be phi k x, and in this case, my lag is going to be 12 m minus 1 plus or minus 1. Well, wait a minute. Hold on. Wait. We just want to make sure I do this right. Oh yeah, of course. Because if m is equal to 1, then I get plus 1 and minus 1, which are both going to be they're both going to be the same thing by symmetry. The auto covariance at a lag of minus 1 is the same as the auto covariance at a lag of plus 1. Okay. Sorry, I was just confusing myself there for a second. So in this case, what we can basically do is use what we did before. Basically, the point is we just keep multiplying by phi. By phi for every multiple of 12. That's an exclamation point because I'm excited, not a factorial. So I'm going to delete that just so it's clear. And what we end up with is an auto covariance. That's going to look like sigma squared
theta phi to the mth power 1 minus phi squared. All right. Now, what else can we do here? Well, we're more or less at the end of what I wanted to talk about here. What I'm going to do is we're going to talk about the autocorrelation so we can get a sense of what the ACF plot should look like if I had this model and I plugged it in. Now, in the next lecture, we're going to spend a lot of time looking at actual data in R and simulated and real data in R and trying to understand how to look at seasonal models. There's a lot to do, so I want to spend a lot of time on that, but dedicate a lecture to data analysis. In this case, let's just try to fight our way through it mathematically. So going back up here, what happened to our variance? Well, our variance way up here is going to be sigma squared, 1 plus theta squared, 1 minus phi squared in the denominator. So let's say consider the ACF, the autocorrelation, because autocorrelation function is one of our friends that's going to tell us a little bit about what's going on with our time series data. If we go back to where we were before, so what we found was that, well, let me write it out because I need to make sure that the variance of xt is going to equal sigma squared 1 plus theta, was it? No, theta squared, yes, of course, because it's just like it is for the MA process, 1 minus phi squared. So if we were to consider the autocorrelation at lag 12 m, well, what's that going to be? That's going to be the auto covariance at a lag of at lag 12 m 1 minus phi squared, and we're going to divide this whole thing. Actually, why don't we just multiply by the reciprocal? We're going to divide by the variance, which is multiplying by the reciprocal of the variance, and we get something that should look like, well, things cancel out. That cancels out, that cancels out, and we're left with just a phi to the mth power 1 plus theta squared. And if we were to consider the autocorrelation at 12m plus or minus 1, well, we'd get the exact same thing, except we'd multiply by theta. So now we'd end up with a theta phi m 1 plus theta squared. So what does this autocovariance function look like? Well, we can plot it out. Let's pretend that both of these are positive because I don't really want to deal with sign flipping. So let's say that theta is equal to, I don't know, 1/2, and phi is equal to, I don't know, 0.8 or something. Okay, so, all right, I'm not going to get this exactly right because of the 1 plus theta squared in the denominator, but effectively what we're going to get is, well, at lag 0, 1, 2, 3, and then we're going to just skip all the way to 11, not to scale, 11, 12, 13, and then we're going to skip all the way to 23, 24, 25, and so on. So what would we expect to see? Well, if we have a value of 1 here, in fact, I'm not going to, well, I'm just going to write phi, so it doesn't really matter that I'm going to give it a magical value of 0.8. So we're still going to have, of course, 1 at 1. That's always the case. When we're offset by a lag of 1, well, now what we're going to get is we're going to get something like theta divided by 1 plus theta squared. In this case, if that's like 1/2 plus well, I'm just going to make up a value. It's going to be something like this. We're just going to pretend that's the value. Maybe I should change the color scheme here, red. Then we're going to get a bunch of zeros, and all the way until we get to 11. And at 11, we're going to have the exact same thing that we had. Well, let's do 12 first. At 12, we're just going to have the usual auto covariance thing, where what we do is we decrement by multiplying by phi. Phi is less than 1. So we're going to get something a little bit smaller here. Let's switch to red because I kind of like, maybe we'll get something like this. And then to the left and to the right, we're going to multiply by theta, which is 1/2. So we'll have half strength at those. And then we're going to get some other decrement at 24 and half strength here and here. So what are we getting? Well, we're getting a geometric decay that is going to continue onward from at multiples of 12, but at all the offsets, we're also going to have a similar little pattern. So this is something you might see in practice, right? You plug in your you plug in your data to the auto covariance function in R, and what you see are these little spikes. And maybe it looks like not just a single spike at various lags, but you see a few spikes centered around maybe every multiple of 12 or otherwise. And then this is a pretty strong indicator that you have a seasonal model. So the takeaway is we can look for seasonal trends via the ACF function. So as usual, the ACF function is really nice for exploring time series data and trying to understand what in the world is going on when you have a time series that you're actually working with. If you see something like this where it kind of vanishes, then comes back, then vanishes, then comes back, that's a pretty good hint that there's a seasonal component to your data, your time series. Similarly, if one of the coefficients, like phi in particular, had a negative sign, then these spikes would flip below the axis and above and below. They're still going to geometrically decay to 0, right? So if phi is not that big, then after a few periods of 12, 24, and so on, the values are going to go to 0 pretty fast. If phi is very close to 1, like my hypothetical 0.8, then it's going to take longer to see that. Well, the signal is going to be stronger, so you're going to see a much stronger signal in the ACF. It's not going to go to 0 as fast. All right, so that is really everything I wanted to talk about with respect to the seasonal Arima process. Now, there's really, again, mathematically, there's not a lot more going on than with just the regular Arima. Again, actually trying to compute things like auto covariances, it's a little more tedious, but roughly it's all the same thing. It's just a more complicated Arima model with different parameters and different offsets. When we're trying to do fitting and forecasting, estimating parameters, model selection, all of the same things we talked about before still hold. The hard part is that we would need to try to figure out what a good seasonal period is. We need to figure out what S is. So typically you can kind of just pick one that makes sense. So there are functions in R that will find one for you if it's not obvious. If you have monthly data, it's probably going to be 12, or maybe it's quarterly, maybe it's every 4. If you have daily data, you might want to look at a period of 7 for every week, or maybe 30 approximately for every month. Now, months are weird because they don't all have the same number of days, but these are the things that you can kind of look at, and you can use intuition about the data that you have at hand to try to take a good guess at what the season should be. It's atypical that you would have a data set with no idea what the season is, and you just have to try like tons of different seasons. But it could be the case, and luckily there are functions that will try to find a season for you. And we will look at all of those, how to do estimation, how to do forecasting, everything in R, look at some cool data sets. But we're going to save that for the next lecture. So I will see you there.